Now we begin chapter 2, Metric Algebra. From the elementary school, you have learned about numbers and operations such as addition, subtraction, multiplication, division, and factorization. Matrices are also mathematical objects, so you may define metric operations similarly done for numbers. Metric algebra is a study about such metric operations and related applications. The techniques you will learn through this chapter are quite fundamental and important to further develop for application tasks. Let's go to the first section of the chapter, metric operations. A is an m by n metric, as in this figure. We'll name the entries by using here Aij. That is the entry in row I and column J. That is row direction, so it's ith row. And there is column direction, so jth column. So the entry in row I and column J is that one. We'll name the entry by Aij. So we write down in this way, A is Aij. So we can access the entry by choosing ith row and jth column. Here we have terminologies. If m is the same as n, then the metric A is called a square metric, because the number of rows and number of columns are the same, then it looks like a square. So we call it a square metric. If A is an n by n metric, a square metric, then the entries A11, A22, up to AN are called diagonal entries. Here, once M and R are the same, then along the main diagonal, the entries are called diagonal entries. A diagonal metric is a square metric whose non-diagonal entries are zero. That means that except the diagonal entries, everything else is zero. Then we call the metric a diagonal metric. For example, the identity metric is a diagonal metric. And also we'll use the notation here. The first column is indicated by using boldface A, sub 1, and in general, jth column will be notated by A sub j. Okay, here we'll define metric sum and scalar multiple and metric multiplication. Two matrices A, B of the same size are equal if and only if the corresponding entries in A and B are equal. First of all, two matrices should have same size and the corresponding entries are equal. Then we say the two matrices are equal. The sum of two matrices, A and B, of the same size, of course, in summation also, two matrices must be of the same size. Then you can add here. So AB, A plus B, is same as Aij plus Bij. That means that Ij entry of this addition is coming from Ij entries of each metric and added in this way. Now scalar multiplication, and if R is any scalar, then here Ra is just R Aij for each entry R is multiplied. Let's see example here. Okay, A, B, C, three matrices are given, and we'll try to add and do some scalar multiplications. Okay, for instance, we start with A plus B here. Okay, and A plus B, that is, now we have here A and B, and they have the same size, so that in this addition we try to add the corresponding entries. So first 4 and 1 is added for this position, so it's 5, and this one 0 plus 1 is 1, 5 plus 1 is 6. Okay, now second row, minus 1 plus 3 is 2, and 3 plus 5 is 8, and 2 plus 7 is 9. Okay, that is A plus B. How about A plus C? And A has 3 columns, but B has only 2 columns, so that we cannot add them. So there is no such addition possible. Okay. Now, how about A minus 2B? And that can be done quite easily. Okay, A minus 2B. Then here we write down here A 4, 0, 5, and minus 1, 3, and 2. That is A. And here minus 2 can be here multiplied inside. So that is a scalar multiple. Okay, let's try to multiply 2, then 2, 2, 2, and 6, 10, 14. Right? Now, the subtraction can be done by subtracting corresponding entries. So that here 4 minus 2 is 2, 0 minus 2 is minus 2, 5 minus 2 is 3, and so on here. Minus 1 minus 6 is minus 7, 3 minus 10 is minus 7 again, and 2 minus 14 is minus 12. Okay. Okay. It's quite simple. Now we'll go to metric multiplication here. A is m by n metric, and B is on m by p metric with columns B1 to BP. Then the metric product AB is on m by p metric with columns AB1 up to ABP. That means that for the product, the multiplication, now B has P columns, so that B is replaced by here its columns, and now the product is defined in this way. Here, that is basically collection of metric vector multiplications. A B1 is the first column, A B2 is the second column, A B3 will be the third column, and so on. So that is the definition. So here, eventually, the metric multiplication is a collection of metric vector multiplications. Okay. Okay, here metric multiplication as a composition of two linear transformation, and we'll try to measure action of metric, the product AB, on vector X. And then here ABX, and then first we apply B to X, and then later on A multiplication. So start from X, multiplication by B will make BX, and again multiplication by A we will reach at ABX. Let's try to see detail of this metric vector multiplications, the composition of two linear transformations. Okay, A is in n by n. Now B is in n by p. Then X is vector in Rp. Then, okay, Bx, that is, earlier we learned that Bx is can be written in this way, linear combination of the columns of a B. So B has columns and X, so that it can be written in this way. Now we multiply A, then Bx is now here, so that A is linear transformation, so that you can apply A to each here the vectors, each vector, so that we can reach at here now x1 A b1 and x2 A b2 and so on. Now again, this linear combination can be written in this form. AB1 is your vector, so that we collect these vectors and X here. If we look at from the beginning to end, then ABX, so action of AB on X is given in this way, so that AB, the product must be same as this one. That is this conclusion. AB is now the collection of metric vector multiplications. The vectors are coming from the metric B. Okay, so we have such conclusion, and along with this example, we can define metric multiplication. But first we defined in this way, and this is interpretation of the definition. Okay. Now here we have to be careful, and in this computation, and here AB1 is possible only in this case. Here now A is given, and now a vector is multiplied, then number of entry here and number of entry here must be the same, so that A is on n by n metric and B is on n by p metric. This n must be the same. Without that, it's impossible. Okay. Okay. Here, T is a transformation from R2 to R3, and S is now R2 to R2, such that T of X is AX, and A is given over there. S of X is BS, BX, and B is given in this way. Compute the standard metric of T as composition. Okay. Here we have a hint, but this is almost the solution. Okay. From the definition, T composition S of X is same as S of X and later T application, but S of X is now B of X. Okay, now T of X is A multiplication, so that we multiply A. So we can rewrite in this way, and the composition action on X is the same as AB multiplication on X, so that the standard metric for the composition must be A times B. Right? Okay. B is the standard metric for S, and T is the standard. Okay, A is the standard metric of T. So you have to keep the order same. T composition of S is standard metric must be A times B, not P times A. Okay. Row column rule for metric multiplication. If the product AB is defined, which means that here number of columns in A, so AB multiplied, then here number of columns in this direction and number of rows in B must be the same, then the product is defined. And now defined n, A is in n by n, then the entry in row I and column J of AB. So after product here we have AB. Now we are considering here now ij position, that is ith row, and now that is here j's column. Then this entry will be AB and here ij. Right? Okay, here is the sum of products of corresponding entries from row I of A and column J of B. That means that ABIJ is now that summation. This is a kind of dot product. Here it means that now here we choose ith row from A and j's column. Then here this row and column and corresponding we multiply entries. First entry, second entry, and then after the product, each corresponding entries, and then sum them, and that is exactly this one. The first one from here, and the first one from this column, and there's this one. This one is the second one in the row, and this one is now second one in the column. And here we after this product we add them, and so that it is a sum of products, and it's often called the dot product. So ith row, j's column, dot product. Okay, so we'll make that entry ABIJ. Okay, we'll continue in part 2. Thank you.